Many of the decisions we make are decisions under risk. When you get in a car, that's risky. That's why we buy insurance. When you buy a stock, you don't know how that's going to turn out, so that's risky. When you take a job somewhere, there are lots of factors involved that might pose some risk. So we need a theory for decision making under risk. And that's what we are considering today, how to model decision making under risk. When we talk about the decision-making theories for risky situations, we often talk about gambles and lotteries. But you have to remember that that's just a convenience. It's an easy way to think about risky situations. Lots of other kinds of situations are risky as well. When you gamble, you're seeking out risk and you're looking to make a decision that you know will involve risk. But a lot of decisions that we make um, involve risk, even though we would prefer if they didn't. So don't be misled by the fact that we often talk about gambles and lotteries when we talk about decision-making theories under risk. We are thinking about any kind of decision that might involve risk. It's just convenient and easy to think about gambles or lotteries because the risk there is really clear and clearly articulated. There are two perspectives at least that we can take when we are thinking about decision making under risk. One could be to think about this person right here who is making a risky choice, and we could think about, well, what's her mindset, what's her thought process, how is she making that choice? So we could take the perspective of the decision maker and ask, well, what should I do in a risky situation? Or we could take the position of an observer who is looking at these people making risky choices and is thinking, how can I model their decision making process, how they make choices? And those are two different perspectives. This one, the observer is much more the social science perspective. So we are thinking, sitting here and thinking, well, we are looking at these decision makers. How can we model their decisions? The other perspective is more practical, and maybe we are looking for a way to make better decisions in risky situations. The decision-making theories that we are developing can be applied in really either perspective here. To start with, consider this gamble. We'll play a game. I'll flip a coin. If it comes up tails, you'll get $1. If it comes up heads, you'll get $3. So either way, you'll come out ahead, which means you should be willing to pay some money to play this game. How much would you pay to play this game? One way to think about the answer would be to consider how much you can expect to win. So you win $1 with probability 1/2 that the coin comes up tails, and you win $3 with probability 1/2 that the coin comes up heads. So overall, you could expect to win $1 with probability 1/2 or $3 with probability 1/2, which comes out to be $2. That expectation comes out to be $2. That's the expected value of this gamble. So you might say, well, I'd be willing to pay $2. That's the expected value of this gamble. All right, let's consider now a different description that maybe will be more convenient going forward of the same gamble. We could describe the outcomes with their probabilities in this way. Probability of the first outcome and then the first outcome. Probability of the second outcome and then the second outcome. So we are really describing the same gamble, just in a more convenient formal way. And we could say that the gamble is worth its expected value. Now consider this very similar gamble. This is a game as well, and I'm going to be flipping a coin. And the way we'll play this is if the coin comes up tails, you'll get $2. If it comes up heads, we'll flip it again. If it comes up tails the second time, you get $4. If it comes up heads the second time as well, we'll flip it again. If it comes up tails the third time, now you get $8, and so on. So the way this works is we'll keep flipping this coin until it comes up tails. And if it comes up tails on the first try, you get $2. If it's on the second try, you get $4. And it doubles every time we flip the coin, your winnings double. How much would you be willing to pay to play? How much would you be willing to pay to play this game? Well, you could think about it the same way as we thought about the previous gamble, and you could start calculating the expected value of this gamble. So let's see, you could win $2, that happens with probability 1/2, or you could win $4. Well, what's the probability that that happens? You get heads and then tails. The probability of that is 1/2 times 1/2, which is 1/4. Or you could win $8. What's the probability that that happens? Well, you have to have heads, heads, tails. That happens with probability 1/2 times 1/2 times 1/2. That's 1/8, and so on. So you get an infinite sum that goes like this: 1/2 times 2 plus 1/4 times 4 plus 1/8 times 8. What does that equal to? Well, that equals to 1 plus 1 plus 1, and so on infinitely. So in fact, the expected value of that gamble is infinite, which would suggest that you should be willing to pay an infinite amount of money to play this game, which seems clearly crazy. So something is wrong here. What's going on? The way we evaluated that gamble was by its expected value. So here's the gamble again. Probability of the first outcome, probability of the second outcome. And this is a general description of a gamble, and the general description of the expected value is probability of the first outcome times first outcome plus probability of the second outcome times second outcome, and so on. This is a finite gamble, so it has n outcomes. We go only up to n, but the gamble we just considered was actually infinite. The St. Petersburg paradox got its name from being presented by Daniel Bernoulli at the Academy of Sciences in St. Petersburg in the 18th century. The resolution that he suggested to the paradox that we just saw was this: instead of expected value, consider expected utility. We have a lottery, just like before, and we evaluated it earlier using expected value. But instead, what if we evaluated it using expected utility? In other words, instead of multiplying the probability of the first outcome by the value of the first outcome, let's multiply it by the utility of the first outcome, and then multiply the probability of the second outcome by the utility of the second outcome, and so on. So add up the probabilities multiplied by the utilities of the outcomes, and that gives you the expected utility of this lottery as opposed to the expected value. The function that we are applying to the outcomes, which are just money values, money amounts of money, that function u is called a utility function, and it maps different amounts of money to so-called utility. So instead of multiplying the probabilities by the outcomes, the monetary outcomes themselves, we are multiplying them by this utility of the outcome, which describes how the decision maker feels about the different amounts of money. The utility function u is called the Bernoulli utility function, and a commonly used Bernoulli utility function is square root of x. That would look like this, and it would map different amounts of money on the x-axis here, so these are different amounts of money, to utilities of different amounts of money. So for example, the first $5 for this decision maker would increase utility by this much, but the second $5 from 5 to 10 would take utility from about 2.5 to about maybe 3.2. In other words, increase utility by a lot less than the first $5 did. In fact, this utility function is concave, and that means that every additional dollar increases utility less than the previous dollar that the decision maker received. So the value of money for this decision maker is decreasing with wealth. And we think that that's usually a fairly reasonable property, and so a utility function of money usually has this kind of concave shape. And in fact, often this particular utility function, the square root of x or some version of the square root of x, is used. So how does this change the outcome of the St. Petersburg paradox? Let's look at that paradox again. Instead of using expected value, now we're going to use expected utility, in particular with this utility function. Instead of taking the probability of the first outcome, which is $2, and that probability is 1/2, instead of multiplying that 1/2 by the $2, we multiply it by the utility of the $2, which is the square root of 2. And instead of multiplying the probability of the second outcome, which is 1/4, by that second outcome, which is $4, we multiply it by the square root of $4, which is the utility of 4, and so on. So we get this infinite sum. If you rearrange that a little bit, or actually just simplify it slightly, then the first term just becomes square root of 2/2, and the second term, which is square root of 4/4, is square root of 2/2 squared. And the third term is square root of 2/2 to the third, and so on. And that infinite sum is equal to 1/2 over the square root of 2 minus 1. And that's equal to about 2.4. So by the way, how do we get that calculation? How do we get that infinite sum equaling this 1/2 over the square root of 2 minus 1? Let's take a quick look at that. So here's the infinite sum that we're looking at. Let's call it x. And so x is what we are looking for. We want to calculate x. Well, let's multiply this infinite sum by 2 over the square root of 2. In other words, let's look at 2 over the square root of 2 times x. The first term becomes just 1. The second term becomes just square root of 2/2. The third term becomes square root of 2/2 squared, and so on infinitely. And then let's subtract x from 2 over the square root of 2 times x. And that's what we do right here. And that means we are subtracting every term here from every term here. And this term is cancelled by this term. This term is cancelled by this term. And every one of these terms will be cancelled. Every one of these terms will be cancelled by every one of these terms. And the only thing that's left is this 1. So this difference is in fact 1, which means we can now solve for x. And if we do that, we get x equals 1/2 over square root of 2 minus 1. Okay, so to the St. Petersburg paradox, and we find that with this particular utility function, the expected utility of this gamble would be 2.4. Does that mean that this decision maker would pay $2.40 to play this game? Not so fast. What we have found is that the expected utility of this lottery that we are looking at is equal to 2.4. That doesn't mean that the decision maker would pay $2.4. That means their expected utility would be 2.4. So the question we want to ask is, what sure amount of money C would that be indifferent to for this decision maker? In other words, what sure amount of money C would have a utility equal to 2.4 exactly? So we want to solve this equation that says the utility of this sure amount of money C is equal to 2.4. The utility function is the square root function, so we look at the square root of C equal to 2.4 and solve that for C, which gives us 5.8, which means that this decision maker would pay $5.80 to play this game, which is obviously very different from infinite. And this is how using expected utility as opposed to expected value to evaluate a lottery resolves the St. Petersburg paradox. By the way, this 5.8, this $5.80, is also called the certainty equivalent of the lottery that we started within the St. Petersburg paradox, because A decision maker with this particular utility function, square root of c for money, would actually be indifferent between getting $5.80 for sure or playing this particular lottery that the St. Petersburg paradox describes.